In this video, we want to talk about the right-hand endpoint rule and how we can use it to compute the area beneath a function, on some interval a to b. So first thing that we do here, given our function on the interval a to b, is we compute delta x. That's the width of our interval, of each of our subintervals, as we set this up. And that would be b minus a over n. That would be b minus a over n. And hopefully at this point you've looked at some of the examples of doing this stuff as we worked out the area beneath y equals x squared between 0 and 4. And now we're kind of generalizing this idea. So you can see a little bit more detail in the notes. Here I'm just looking at working with the formula and then using it. So delta x is b minus a over n. That's the width of each subinterval. And then xi, right, the right-hand endpoint, then would actually be, since each interval has a width of delta x, xi would be I intervals over, so it would be a plus delta x times I. And then the sum of all those intervals, the estimate, Sn, S of n, or S upper n is what I call it in the notes, would be the sum as I goes from 1 to n of f of xi times delta x. F of xi times delta x. So we want to take a look at using this to compute the area beneath a function now. So let's say we want to find the area beneath y equals 3x plus 2 on the interval from 1 to 6. So you could actually graph this one. The graph is actually, since 3x plus 2 is a straight line, you could actually graph that and you'll get actually a trapezoidal shape that we're going to be dealing with here. But we want to use our area approach to do this with sums. So first thing we do is compute delta x. That's b minus a, the difference of the width of the overall interval divided by n. So it would be 6 minus 1 divided by n, which would be 5 over n. Then we compute xi. Xi is the left endpoint, 1 in this case, plus delta x, 5 over n, times I. Now, before we go into the sum formula, what I like to do at this point is go ahead and plug that xi into my function so I can see what f of xi would look like. So f of xi, plugging that in, that would be 3 times xi plus 2. Pretty straightforward. And then what is xi? Well, let's plug that in. So 3 times 1 plus 5 over ni plus 2. And then we multiply through. 3 times 1 is 3, plus 2 gives us our 5. And then 3 times the 5 over ni would give me 3 times 5 is 15 over n times I. So there's my f of xi function. And now I just put this into my sum. Sum as I goes from 1 to n of f of xi times delta x. Getting a little ahead here. So we plug that in. F of xi, there it is, 5 plus 15 over ni, times delta x. And then I just multiply through by delta x to simplify it. So 5 times 5 over n would be 25 over n. 15 over ni times 5 would be 75 over n squared now times I. And at this point, now we have a sum in terms of I, so we can use our summation properties to break this apart. So we have sum of 25 over n, that can be broken off, times 1. So factoring out the 25 over n. And that would be I goes from 1 to n. I'm going to get a little lazy here and leave that off for the time being, because we know it's a sum. Both the 25 and the n again does not depend on I, so it can be pulled out. And then I have the 75 over n squared with the I, so I can write that as 75 over n squared times the sum of the i's. And then we pull our formulas in. Some of the ones, we know that's just going to be n here. And some of the i's, we can use our formula to do that. 75 over n squared times I. So we pull those two formulas out. So we get 25 over n times the sum of the ones. If you add it 1 up n times, that would just be n. And then 75 over n squared times, we pull out the formula for the sum of the i's. That would be n plus 1, all that over 2. And at this point now, we go through and we simplify, and when we do, we'll have an answer in terms of n that'll tell me the value of my sum, my estimate, for any number of subdivisions. Okay. And that's what we do now. The n's cancel out, of course, in the first one there. And so we get 25 times 1, which would be just 25. And then in the second one here, the n's cancel out. The n's cancel out. Nothing else cancels out. So I can take that 75 and put it with the n plus 1. Have 75n plus 75. And then that's all going to be over 2n. Okay, and then I just do a little bit more housekeeping here. I can take 75n over 2n and simplify that. So I have 25 plus 75 halves, because the n's cancel out, plus 75 over 2n. Now that formula will tell me the area for any number of estimate, any size estimate. N equals 4, n equals 8, n equals 1,000,000. That'll give me the estimate. Now we can clean that up. We can call that S our sum. Now we can combine the 25 and the 75 over 2, and I will do that in a moment. But at this point, once we have our formula for the sum, we go ahead and take the limit of that thing. And we take the limit, anything that's left over that's divided by n as n goes to infinity, as we learned in our previous topic with limits at infinity, anything that's divided by n is just going to go to 0. So we're going to get 25 plus 75 halves plus 0. And we can just add that up. 75 and 25 is going to be 125 halves. And so now we found the area beneath the graph of y equals 3x plus 2 to be 125 halves.